last lecture we were discussing the addition of two angular momenta, and we had taken the specific case for J1 equal to half and J2 equal to half. So, we have something like a neutron proton problem. Both have an intrinsic spin angular momentum of half h cross. So, how will they add up? We found that the total angular momentum J will take 1 and 0, and so therefore, we have a total of 4 states, and we wrote down that J1 equal to half. So, therefore, M1 is equal to half and minus half, and J2 is equal to half. So, M2 is equal to plus half and minus half. So, therefore, the M value, which is equal to the sum of the two M1 plus M2, will take the values 1, 0, 0 and minus 1, half plus half, half minus half, minus half, half, minus half, minus half. And then we wrote down, first we wrote down that phi of 1 comma 0, this is common to all, J1 is. So, this is J, this is the first digit is the value of J, and this is the value of M. So, this would be, I am sorry, let me write it down again. This is phi 1 comma 1. So, J value is 1 and M value is 1. So, when M is 1, M1 has to be half and M2 has to be half. So, therefore, this will be equal to psi J1 J2, let me write it down here, half comma half comma half comma half. These are the values, the last two digits are the values M1 and M2. Then what I did was that I operated this by J minus, and I will get root 2 of phi of 1 comma 0, and when I took the root 2 out here, so I will get 1 over root 2 psi half comma half, and this will become J1 minus operating on this will half minus 1. So, this will be minus half and this will be half plus 1 over root 2 psi of half, half, half minus half. So, these coefficients 1 over root 2 which relate the phi functions to the psi functions are known as the Clebsch-Gordan coefficient. Now, if I operate this again by J minus, so as you may recall that J minus ket J m will be J plus m, that is 1 plus 0, and then you will have J minus m plus 1, that is under root of 2. So, again under root of 2 will come, but a little algebra will show that phi of 1 comma minus 1 will come out to be, you have to do a little algebra and I leave that as an exercise, you will find that this will be half, minus half, minus half, and that you should have expected, because when m is minus 1, m1 has to be minus half, m2 has to be minus half. Now, how do I get phi 0, 0? You cannot by operating this by this function j minus or j plus, because the j value cannot change. So, you use the fact that this has to be orthogonal to that. So, you write down phi of 0, 0 will be a linear combination of these two such that it is A normalized and B it is orthogonal to this. So, that is given by 1 over root 2 minus psi half minus half plus psi half minus half. So, we finally actually this the values of J1 and J2 are repeated everywhere, and therefore, one omits them and one writes as psi half. So, let me rewrite this. So, I get phi 1, 1 is equal to psi half, half. These are the values of j and m, and these are the values of m1 and m2, and you have phi 1, 0 is equal to under root of psi minus half plus psi half minus half. Let me leave some space, and then this is phi 1, minus 1, this will be psi minus half, and finally, the singlet state 0, 0 is equal to 1 over root 2 minus here psi minus half plus psi half minus half. I could have easily well chosen plus here and minus here, but as a matter of convention it is chosen minus here, and I will tell you why. This state is often represented as spin up state. So, this is up down, this is up, both are pointing upwards. This is 1 over root 2 down, up, plus up, down. This is down, and this is 1 over root 2 of minus down, up, plus up, down. These three states are the triplet states, and this state is known as the singlet state. Finally, I also write down in the form of a matrix. So, I write down this as phi 1 comma 1, phi 1 comma 0, phi 1 comma minus 1 and phi 1 comma 0 comma 0. This I write as a column matrix. This is equal to a square matrix, and then I write this as psi half half, which is up up, and then second one will be psi half minus half, and then psi minus half half, and psi minus half minus half, and the coefficients will be 1 0 0 0 0 1 over under root of 2 1 over under root of 2 0, third one will be 1 minus 1. So, that is equal to this. So, 0 0 0 1, and this will be 0 1 over root 2 and minus 1 over root 2. These coefficients, which are represented by this square matrix, are known as the Clebsch-Gordon coefficients. Okay. Let me give you another example. I hope this is clear. So, we consider the case, the hydrogen atom problem, the spin orbit interaction. So, we assume that J1 is equal to L is equal to 1. So, as we know that the wave function, the hydrogen atom wave functions are say n is equal to 2 state. So, this is RNL, that is R21 of R Y1 M. This is the theta phi, where M can take values 1, 0 and minus 1, and then you have the spin up S is equal to half. So, the M2 value, this is J2, M2 value can take half and minus half. So, therefore, we start with the ket phi J1 J2 I forget. So, that is 1 comma half, and as I told you that the maximum value of M is, you see M1, sorry, this is M1. So, M1 is 1 0 minus 1. So, the maximum value is 3 by 2. So, the J is 3 by 2 and M is 3 by 2. Okay. So, this is the J value and this is the M value. Now, this is equal to the psi function corresponding to 1, this is J1, this is J2, and M1 and M2 must be equal to 1 and half. Because M1 plus M2 must give me 3 by 2. Now, in order to get the Clebsch-Gordon coefficients, I must operate this by the operator J minus. So, J minus will be J plus M. So, 3 by 2 plus 3 by 2 is square root of 3, and then J minus M plus 1, that is just 1. So, if I operate this, if I operate J minus on this, so I will get phi 1 comma half 3 by 2 and then half, and this will be, this is J1, this is J2. So, J minus is equal to, on the right hand side I operate this by J1 minus plus J2 minus. So, I will have, so if I operate this by J1 minus, so this will be J1 plus M1, that is square root of 2 and then M1 will decrease by 1. So, this will be psi 1 half 0 half plus, if I operate this by J2 minus, so this will be half plus half, that is 1, and J2 minus M2 is 0 plus 1. So, that is just 1. So, this will be psi 1 half, this will be 1 and this will be minus half. So, please see, M1 is 0, M2 is half. So, M is half automatically, M1 is 1. So, here now the Clebsch Gorton coefficients are square root of 2 by 3. If I divide this by, so if I take this on this side, so square root of 2 by 3 and 1 over root 3. These are the, and if I operate this again, I will get 3 halves and I leave it as an exercise minus half. So, I will get an expression for phi, no, I leave that as an exercise, that is very simple. So, you will operate this by J minus, if I operate J minus on this, I will get here, so half to minus half. So, then it will become 0 and minus half and minus 1 and plus half. And again we will be able to get Clebsch Gorton coefficients. Let me write down the exact wave functions. Please see, this is L is equal to 1 and M is equal to 1. So, this will be, and this is the spin up state or Z up state. So, R 2 1 of R, Y 1 1 multiplied by 1 0. This wave function is known as the Pauli wave function corresponding to this state. So, therefore, the Pauli wave function for the, say, n is equal to 2 doublet, L is equal to 1, that is P, and I have taken 3 by 2. And for M is equal to 3 by 2, when J is equal to 3 by 2, then M can have 3 by 2, half, minus 3 by 2. So, the Pauli wave function is, this is known as the Pauli wave function R 2 1 of R, Y 1 1 0. Let me do the second case. So, this is the Pauli wave function corresponding to M is equal to half. So, the phi function corresponding to 1 half, 3 halves half will be, the Pauli wave function will be square root of 2 by 3, please see this, 1 0. So, therefore, n is 2. So, 2 1 of r y 1 0 and the spin up state, that is 1 0, plus square root of 1 by 3 r 2 1 of r y 1 1 and then the spin down state, that is 0 1. So, therefore, the Pauli wave function will become under root of 2 by 3 r, actually r can take r 2 1 r outside, r 2 1 r y 1 0 and under root of 1 by 3 r 2 1 of r y 1 1. Now, I leave it as an exercise for you to show that phi, if I operate this by j minus operator, then I will get phi 1 comma half 3 halves, and if I operate this by j minus, half will reduce to by 1. So, this will be minus half. This will come out to be r 2 1 of r if I take outside, and I leave this as an exercise for you to show. This will be square root of 1 by 3 y 1 comma minus 1 of theta phi, these are the spherical harmonics, and then square root of 2 by 3 y 1 comma 0 theta phi. Now, you should understand that this is the value of m. So, that must be equal to m 1 plus m 2. So, m 1 is minus 1 and this is the spin up state. So, m 2 is plus half. So, minus 1 plus half is minus half. This multiplied by the spin down state. So, because this is in the second row. So, 0 minus half. So, this is this. Now, you can in this way you can take L is equal to 2 and L is equal to 3 and you can take any function and L1, L2. You first have to start with the fact that phi, you have to first start phi J1, J2, J and M. So, the maximum value of M maximum is J1 plus J2, because the maximum value of M1 is J1. So, the maximum value of J is also J1 plus J2. So, therefore, phi J1 comma J2, now understand this, this is M1 plus M2 comma M1 plus M2. This will be equal to psi of J1 J2 then M1 M2. Oh, sorry, I am sorry. The maximum value of M1 is J1. So, therefore, phi J1 J2 J1 plus J2, this is the maximum value of J, and the maximum value of M is J1 plus J2. This must be equal to psi J1 J2, and the maximum value of M1 is J1 and the maximum value of M2 is J2. So, one must always start off with this equation. Sorry, let me cover this up. So, if J1 is 1 and this is half, then this is 3 by 2, 3 by 2, and this will be 1 and half. I hope you. So, let us suppose J1 is 1. So, 1 comma half, this is 3 by 2 comma 3 by 2, and this will become 1 comma 3 by half. So, 1 plus half is this. So, there will be only one function like that. Now, you keep on operating this by j minus, j minus, j minus, and you will get the all the Clebsch coordinate coefficients. And finally, if you keep on operating this, then the last function will be phi j1 j2 j1 plus j2, this is the j value, and the minimum value of m will be minus j1 minus j2. This is the minimum value of m. This will come out to be psi j1 j2 minus j1 minus j2. So, m1 will be minus j1 and m2 will be minus j2, and in between you have to operate a large number of times by the j minus operator. In almost all books, the table is given. So, for example, for an arbitrary value of j, j1, let us suppose j2 is equal to half, then this table gives us the values of the Clebsch coordinate coefficients. Let me take an example. Let us suppose j1 is equal to say 1. So, the j value can be either 1 plus half or 1 minus half, that is 3 by 2 or half. Okay. So, this will be, this tells us that the phi function. So, let me take 3 by 2. So, j1 is equal to half and j2 is equal to, j1 is equal to 1 and j2 is equal to half. So, you have phi j1 is 1, j2 is half, j is let us suppose 3 by 2, and let us suppose m. Then this tells us that this is j1 is equal to, so 1 plus half 3 by 2 plus m, two into 1 plus 1, that is 3. This will be multiplied by psi, m2 is half. So, m1 will be m minus half. So, psi j1 j2, that is 1 comma half, and m1 must be m minus half plus this number. This is how to use the Clebsch coordinate, the table corresponding to Clebsch coordinate coefficients. So, this will be 1 plus half, that is 3 by 2 minus m divided by 3 psi of 1 comma half m plus half minus half. So, this will, so j1 is equal to 1, these are the wave functions. For example, m is equal to, let us suppose, let me consider the case when j is equal to 3 by 2 and m is equal to half. If m is equal to half, then you will have the Pauli wave function phi 1 comma half comma 3 by 2 half. So, you will have 3 by 2 plus half is 2. So, this is 2 by 3. So, psi 1 comma half m minus half, m is half. So, this is 0 half plus 3 by 2 minus m, m is half. So, 3 by 2 minus half is 1 under root of 1 by, these are automatically normalized, psi 1 comma half, m is half. So, half plus half is 1 minus half. So, always remember that 0 plus half is half, 1 minus half is half. So, this will tell you, this will have that let us suppose we consider the state n is equal to 2, j 1 is equal to 1. So, L is equal to 1. So, we will have square root of 2 by 3 r 2 1 of r, y, if we take hydrogen atom wave functions, y 1 0 spin up state. This is the spin up state plus under root of 1 by 3 r 2 1 y 1 1 spin down state. So, this is my 1 0 state and this is the 0 1 state. Similarly, you can take another example. Let us suppose j 1 is equal to 2. If j 1 is equal to 2, then j can take 2 plus half and 2 minus half, 5 by 2 and 3 by 2, and you can immediately write. Let me just write this up and then, so we will have, so if j 1 is equal to say L is equal to 2, so we will have 2 plus half, 2 plus half is 5 by 2. Let me consider the 5 functions corresponding to so j 1 is 2, j 2 is half, this is 5 by 2, and let me consider the function corresponding to m is equal to half. Let me consider half. So, m value, let us suppose it is half. So, this will be equal to, this will be under root of j 1 L is 2, that is 2 plus half, that is 2 plus 1 is 3, and this is 2 into 2. I hope I am doing the algebra correctly, 3 by 5, and this will be psi, please see this, 2 comma half, 2 comma half, and m 1, m 2 is half. So, this should be 0, because this plus this must be equal to this, plus this number is j 1 is equal to 2 minus half plus half, that is 2 by 5. So, it is normalized, square of this plus square of this is 1. So, this is psi 2 comma half comma m 2 is minus half. So, if m 2 is minus half, m 1 has to be plus 1, because this plus this must be equal to this. So, this is my Pauli wave function. So, the wave function will come out to be very simple. So, the corresponding Pauli wave function will be square root of 3 by 5. Let us suppose n is 3. So, r 3 2, L is 2, and this will be y 2 0 spin up state, that is 1 0 plus under root of 2 by 5 r 3 2 y 2 1 spin down state. So, you have therefore, this will be the corresponding Pauli wave function is square root of 3 by 5 r 3 2 y 2 0 under root of 2 by 5 r 3 2 y 2 1. One can go on and using this table that I had shown, I leave it as an exercise for you to show that for j 1, say let me consider the case when n is equal to say 5, j 1 is equal to let us suppose 3 and j 2 is equal to half, So, the value of j will be either 3 plus half or 3 minus half. So, let us suppose I take 3 minus half. So, this will be, let j be equal to 5 by 2 and m is equal to 3 by 2. Calculate the Pauli wave function. Similarly, you can have j is equal to 7 by 2 and m is equal to say 5 by 2. Calculate the Pauli wave. You can frame any number of problems using that. So, I have given you the complete theory of calculation of the Clebsch-Gordan coefficients. You start with the maximum value of j and the maximum value of m, relate to the corresponding psi function, which are simultaneous eigenfunctions of j1 square, j2 square, j1z and j2z. And the constant coefficients which relate, this is an unitary transformation. You go from one set of unit vectors to another set of unit vectors. The coefficients which correlate from one set of functions to the other set are known as the Clebsch-Gordan coefficients, and I have given you the recipe for calculating that, and also in most cases one has to use this particular table to calculate the Clebsch-Gordan coefficient. This corresponds to J t is equal to half. In many books J t is equal to 1, including in our book, and of course, that is the table has been taken from Conradon and Schottler. For J 2 is equal to 1, the tables are given. The point that we should remember that that the value of j goes from the value, if j 1 and j 2, the value of j will go from j 1 plus j 2. I am assuming j 1 is greater than or equal to j 2. So, j 1 plus j 2 in units of 1 to j 1 minus j 2. Okay. Our next thing that we would like to discuss is one of the most fascinating topics in quantum mechanics, and that is the JWKB approximation. I will just outline you the method that we will develop, and we will discuss the details in our next lecture. So, this method, this approximate method was first put forward by Jeffreys around 1887 or 89, and then when quantum mechanics was developed in 1926, this method was simultaneously published by Wenzel, Kramers and Brillouin in the year 1926 itself. Many books write this as WKB approximation, but since it was Jeffreys who first put forward the method as a mathematical solution to a differential equation, I think it is appropriate, and many people do that, to write this as the JWKB approximation. Now, our Schrodinger equation, the one dimensional Schrodinger equation, is in the form of d2 psi by dx square plus 2 mu by h cross square E minus v of x psi of x is equal to 0. So, this function is a known function of x. So, we denote this by k square of x. This is also a wave-like equation. Even in plasma physics or electromagnetic theory, we have, when an electromagnetic wave propagates through an inhomogeneous medium, we have a wave equation, we have an equation like this, plus omega square by c square n square of x psi of x is equal to 0. where n square of x, omega is the angular frequency of the wave, c is the speed of light in free space, and n square is the square of the refractive index. So, in many problems, even in waveguide theory, you have an equation which has of the form d2 psi by dx square plus k square of x psi of x is equal to 0. Now, the WKB, the JWKB approximation gives us an approximate solution of this equation when k square of x does not vary too much. So, we will develop this. So, in the Schrodinger equation case, k square of x is equal to 2 mu by h cross square E minus V of x. In a plasma physics problem, it is omega square by c square n square of x. In waveguide theory problem, it has a different expression, but in each case it is a function of x. Of course, here as you can see that if E is less than V of x, then k square will become negative. We will discuss the solution when k square becomes negative. But right now let us assume that k square is positive and it is a slowly varying function. Slowly varying function. What is meant by slowly varying? I will explain in a moment. It does not vary too much, that is, if I plot k square of x, it varies slowly, something like that, and it does not go through any zeros or something like that. And so, we are not considering functions k square of x which are very rapidly varying functions. That is the, we will show that, we will derive the condition for the validity of the WKB, JWKB solutions. So, in the first approximation, let us assume that k square was totally independent of x. So, if k square is totally independent of x, that is independent of x, so k square psi of x is equal to 0. If this is not a function of x, then we know the solutions. I can write down in terms of sine cosine or I k x e to the power of I k x. So, where k is the under root of this and x is of course. So, this suggests that let us try out, let us try a solution of this form e to the power of I u of x. So, psi is given by e to the power of I, say some constant a into e to the power of I u x. So, let me brute force differentiate. So, psi x I assume a into e to the power of I u x. So, d psi by dx, which is psi prime of x, will be equal to a, and then if I differentiate this, so I get I u prime psi of x. If I differentiate this again, so you get psi double prime is equal to I u double prime psi of x plus I u prime psi prime of x, but psi prime of x is I u prime. So, this will be plus I u prime whole square psi of x. I hope you understand. So, I substitute this here, I still do not know what is u. So, I substitute this in this equation and I will get I d2 u by dx square, psi of x will cancel out with every, I square is minus 1 minus du by dx whole square plus k square. So, I substitute this in this equation and I obtain this. I must mention that if I am able to solve this equation, then this will be a rigorously correct solution of this equation. So, I am assuming k square to be a function of x. Once again, that if I assume of this equation a solution of this type, then I obtain that u of x satisfies an equation of this equation. If I am able to solve this equation, then this will be a rigorously correct solution of this equation, because I have not yet made any approximation. Now, when k square of x is independent of x, then this tells us that u of x is equal to k times x, k times x. So, u double prime, so u prime will be k and u double prime will be 0. This suggests that if k square of x is slowly varying, then let me in the first place neglect this term. If I neglect this term, then I will obtain du by dx whole square. If I take k square outside and minus minus sign, so this is k square, or du by dx is equal to plus minus k of x, and so therefore, I can integrate this and I obtain u of x is equal to plus minus integral k of x dx. Thus, since I had assumed the solution of the form of e to the power of I u x, then we obtain the 0th order solution as psi 0 of x is some constant, let us suppose a, e to the power of plus minus I integral x k of x dx. This is known as the 0th order JWKB solution. Okay. The only thing that I have done is neglected the second derivative here, neglected the second derivative of u. Other than that, that is the only approximation that we have made. Now, let me find out what is the equation that psi 0 satisfies. So, let me differentiate this. Let me just take the plus sign. So, you get, so if I take the plus sign, let me write it down again, that psi 0 of x is equal to, I can do it with the minus sign also, plus I integral k of x. Therefore, this is known as, here in this approximation only the phase changes, and so therefore, this is also some people call is as the phase integral method. As the beam propagates, only the phase changes, and therefore, many people call this as the phase integral method. So, let me find out what is the equation that psi 0 of x rigorously satisfies. I have here d psi 0 by dx. If I differentiate this, so this will be the differential coefficient of this will be k of x. So, this will be plus I k of x times the entire quantity psi 0. If I differentiate this again, then I get d2 psi 0 by dx square. So, this is equal to plus I dk by dx psi 0 plus psi 0 prime plus I k times psi 0 prime, and d psi 0 by dx is I times k. So, this becomes minus this thing into psi 0. So, this becomes minus k square, and if I take this also on this side, so you have d2 psi 0 by dx square plus k square minus I dk by dx psi 0 Thus, please see that this solution is a rigorously correct solution of this equation. Equation 1 is a rigorously correct solution of equation 2. But what we wanted is the solution of this equation d2 psi by dx square plus k square psi is equal to 0. So, therefore, if this term, the magnitude of this term is very small compared to this term, to k square, then our solution should be reasonably good. Once again, this function psi 0 of x is a rigorously correct solution of equation 2, but what we had wanted to solve was this equation, and therefore this will be an accurate solution of equation 3, provided we are able to neglect this term. That means the dk by dx must be less than k square, and therefore, we write down that the condition for validity of the JWKB solution, the 0th order JWKB solution is that dk by dx mod square is less than k square, or 1 over k, no I am sorry, 1 over k dk by dx should be less than k of x. This is the condition for the validity. That is, k of x should not vary so rapidly that 1 over k dk by dx is less than k of x. In optics or in electromagnetic theory, when I apply that k square of x is equal to omega square by c square n square of x, and therefore, this is equal to 4 pi square by lambda square, lambda 0 square by n square. This condition means that the refractive index should not change too much in a distance of the order of wavelength. So, that is the condition for the validity of the 0th order WKB approximation. So, in our next lecture, what we will do is try to improve on this solution and develop what is usually referred to as the first order WKB solution. And in fact, people use just the first order WKB solution, and we will then use these solutions to solve the one dimensional Schrodinger equation. These solutions are extensively used in not only in quantum mechanics, but in many diverse areas of physics. Thank you.